Hello everyone, this is Sir Aris. Today we will talk about the residue theorem and methods of finding residues. The residue theorem, um, okay, before that, so let Z not be an isolated singular point of Fz. We are going to find the value of Fz, our integral, close integral of Fz dz on the contour C around the simple closed curve C surrounding Z naught but enclosing no other singularities. Let us expand Fz in Lorentz series about Z equals Z naught. Take note that this part, the A part of the series, is analytic. So if you want to take the integral of these terms, or let's say the sum of all n of a n z minus z naught squared, or n to the power of n, this is equal to 0 from Cauchy's theorem. But for this part, we know that it is not 0. Again, that's from Cauchy's theorem. For the B series, let us consider integral of a Bn term, any term for any value of n. We replace the integrals around C by integrals around circle C prime with center at Z naught and radius rho. So along um, C or C prime, we set Z equals Z naught plus rho e I theta, and the derivative dz is rho I e I theta. So our integral along C of Bn z minus z naught n dz. Our c is now replaced by c prime, where it is a circle, so the integral is from 0 to 2 pi as we vary theta. So that's bn over denominator is z minus z naught, so that's rho e I theta n. Dz is rho I e I theta d theta, and this is bn I um, rho e I naught and rho e I naught. I This is not I theta. So rho e I theta. One of this will cancel the one of the n's here, so we have I over rho e I theta n minus 1 d theta. And we can also write this as I bn over rho n minus 1. So that's rho to the power of n minus 1. Integral of I divided by e I theta to the power of n minus 1 d theta. So this integral is basic. If you can check for n equals 1, the integral um, on C of bn over z minus z naught n dz would be equal to this ibn over rho n minus 1. Just do this integration. Why is this an I here? This is just 1. Okay. So that's e I theta to the power of minus n plus 1 divided by e, oh no, minus n plus 1, evaluated from 0 to 2 pi. So if um, if there is an error here, for sure the answer will be proportional to the ei theta, and ei theta, for theta equals 2 pi, that would be 1, and for theta equals 0, that's also 1. So the um, the limits would cancel out, and this is equal to 0. For by the way, this is supposed to be n not equal to 1, so that for n equals 1, this is simpler. So here, if we start from this part, for n equals 1, this would be 1. This is 0, so this would be 1. And I, you can factor out I. Um, Integral of d theta is theta from 2 pi, from 0 to 2 pi, that's 2 pi. So this would simply be I bn, um, 2 pi. By the way, let me remove that. I put that c here. So I bn, um, times 2 pi, where n is already 1. So let me write here as 1. I removed the erasure here. 2 pi. So by definition, b1 is called the residue of fz. So if you take the integral of fz dz, that's equal to 2 pi I times, so it's 2 pi I times the residue b1 at the singular point c, inside c. If there are many isolated singularities, say z0, z1, z2, and many more, we draw small circles about each. Fz is analytic in the region between C and the circles, but not inside each circle. So if it's analytic from Cauchy's theorem, the integral counterclockwise plus the integral around the circles clockwise is 0. What that means is, if we start our integration here, so we go counterclockwise, but then here we cut this and then go around clockwise around this C knot. And then in return, we go back to C, and then run counterclockwise. Then we make a cut here again, and then we go around, and then another cut here, and then go on with C. And then from here, we make another cut, go around C1 clockwise, and then go back to that cut, and then integrate, go back to the original position. So in this region, excluding the circles, the integral is 0. So for the integral around each circle, that's 2 pi I times the residue. So if you integrate around this circle, that's the answer would be 2 pi I times the residue at this, in this, or uh, at the singular point, so at z naught. So in total, if you want to take the integral over all this region, we simply add. So the residue theorem states that if you want to take the integral fz dz under closed contour C, is equal to 2 pi I times sum of the residues of fz inside C. The integral around C is in the counterclockwise direction. There are several methods of finding the residues. For example, the most basic would be a Lorentz series. In the Lorentz series, if we can reduce the Lorentz series, the residue is just the coefficient of b1 of the term 1 over z minus z naught. For example, find the residue of this function ez over z minus 1 at z equals 1. So let's call the residue r of 1 at z equals 1. So what we can do, um, we th- we know that the expansion of ez about z equals 0 is, so ez equals 1 plus z squared over 2 factorial and so on. But we don't need expansion about z. What we want, so we want um, to expand e z minus z naught. Okay, or actually, to be specific, z naught is 1. So z minus 1 about um, or in powers of z minus 1. To do this, we write our ez as something with e z minus 1, or ez over z minus 1, full expression. Something with ez minus 1. So in this case, to retain this ez here, we should multiply it with e divided by z minus 1. So you have e over z minus 1, and then expand the um, this exponential, that becomes 1 plus z minus 1 plus z minus 1 squared over 2 factorial and so on. So here we can also write that as e over z minus 1 plus um, e and so on. So the only term with a z minus 1, oh, in the denominator is this, and that is actually our, the coefficient e is our b1. So we want that the coefficient of this term, 1 over z minus z naught. Z naught is 1. So um, the residue is the coefficient of 1 over z minus 1, or r1 equals e, this one. Another method is by finding a simple pole. The Lorentz series, given by this expression, a pole of order n is defined as follows. If bn is not equal to 0, but all the b's after bn are 0, fz is said to have a pole of order n at z equals z naught. If n equals 1, we say that fz has a simple pole. So if it has a simple pole, that b1 is still the residue. So what we do, we can find the residue by multiplying fz by z minus z naught. So if it has a simple pole, all of these terms cancel. So from here, it will cancel. So we multiply by z minus z naught, both sides. So this z minus z naught would cancel, and all of this will have an extra z minus z naught. The next step is to evaluate at z equals z naught. If you evaluate z equals z naught, this becomes 0, 0. All of this becomes 0. And we get the value of b1. Example, find our residue at minus 1/2, and r5 for this. Okay, so multiplying, first step, we multiply fz by z plus 1 half. That would give you z plus 1 half fz equals z times z plus 1 half divided by 2z plus 1, 5 minus z. And this would be, so you have z plus 1 half. The denominator, let's factor out this 2 here. So 2z plus 1 half, 5 minus z. So this 2 cancels. Next step, we evaluate to get our minus 1 half. We just substitute z, or the z is here, by minus 1 half. So you have minus 1 half times, or divided by 2 times 5 minus negative 1 half. Okay, so this is minus 1 divided by 2 times 2, that's 4. Um, you have 5 plus 1 half, so that would be 10 plus 1 over 2. So r of minus 1 half is equal to, so 4 divided by 2, that's 2. 2 times 11, that's 1 over, negative 1 over 22. Okay, for r5, or to get r5, multiply fz by z minus 5. So you have fz times z minus 5, that's equal to z times z minus 5. Okay, z times z minus 5 divided by 2z plus 1 times 5 minus z. Take note, there's z minus 5 here and 5 minus z. Divide them, you got negative 1. So you have negative z over 2z plus 1. And then r of at 5 would then be negative 5 divided by 2 times 5 plus 1. So 2 times 5 is 10, 11. So you have negative 5 over 11. Sometimes we may have to evaluate an indeterminate form. So in general, we write r at z naught equals the limit as z approaches z naught of z minus z naught times fz. For example, find the residue of cotangent z at z equals 0. So r 0 would simply be, you take the limit as z approaches 0 of z times cotangent z, which is cosine z divided by sine z. Okay, if we plug in 0 on z, this becomes 0 divided by 0, indeterminate. So we can use L'Hopital's rule. Using L'Hopital's rule, you take the derivative of this, that's cosine z minus z sine z divided by cosine of z. Okay, this is from L'Hopital's rule. So if we substitute z by 0, this becomes 1, this is 0, and this is also 1, so r 0 equals 1. Another example, find the residue at z equals I of this. So you multiply both sides by z minus I, and then evaluate at z equals I. So r at I, let's just write it directly, is the limit as z approaches I of z minus I times sine of z divided by 1 minus z to the power of 4. Plugging in directly, um, I on z, so this becomes 0, this is 0, so that's in indeterminate form. We take the derivatives again using L'Hopital's rule. You have z minus I times cosine of z plus sine of z divided by negative 4z to the power of 3. Evaluating at I, this becomes 0, so you have sine of I divided by minus 4I to the power of 3. Using um, the formula of sine z equal to eiz minus e to the minus iz divided by 2, we have sine of I is equal to eiz minus e minus I. um, z is already, so we use I minus e minus I times I divided by 2. I times I is minus 1, minus I times I is 1. So this is e to the minus 1 minus e to the 1 over 2. So you write Ri as um, here e to the I to the minus 1 minus e to the power of 1 divided by something is missing. There's a 2i here. So over 2i times 1 divided by negative 4i cubed. This 2i times negative 4i, that would give you e minus 1 minus e1 over 2 times 4 is 8, I to the power of 4, that's 1, so you have minus 8, or e to the power of 1 minus e to the minus 1 divided by 8. Now using um, the hyperbolic sine, um, sine or sinh z equals e z minus e to the minus z over 2, Ri is equal to, so remove the 2 here, it becomes 1/4 of sinh 1, hyperbolic sine of 1. Now suppose you have multiple poles. When fz has a pole of order n, we can use the following method for finding the residues. First, multiply fz by z minus z naught m, where m is an integer greater than or equal to the order n of the pole. Next is differentiate m minus 1 times, divide by m minus 1, and evaluate the resulting expression at z equals z naught. For example, find the residue at z equals pi of fz equals z sine z divided by z minus pi cubed. So here we take m equals 3. So by looking at it, we can easily think that 3 might be the pole, so we use it. Um, First is to multiply both sides by z minus pi 3, and then differentiate the result m minus 1 times. Okay, so differentiate m minus 1. So m minus 1 is, let me write it, differentiate m minus 1, which is 2 times. So you have d squared dz squared of z minus pi cube f z, or d squared by dz squared of z sine z. That's equal to the first derivative of sine z plus z cosine z, or that's equal to cosine z plus cosine z minus z sine z. Okay, and then the next step would be, um, after differentiating, divide by m minus 1 factorial and evaluate the resulting expression at z equals z naught. So divide by um, m minus 1 factorial. That's 3 minus 1 factorial, or 2 factorial, or 2. Okay, so divide this by 2 and then evaluate the expression at z equals pi. So you have r at pi equals divide by 2 factorial of our second derivative of z sine z, all evaluated at z equals pi. So you have 1 over 2 of cosine z plus cosine z minus z sine z, evaluated at z equals pi. So you have 1/2 of, at z equals pi, this is minus 1 minus z at sine z, or pi times sine pi is 0, so this is 0. Minus 1 minus 1, that's minus 2, divided by 2, so r pi is equal to minus 1.